everybody, so in this video we are going to talk about a theorem that's related to the mean value theorem. We're going to prove this theorem and then we're going to look at an example of how to use this theorem. Okay, so the theorem says if f prime of x equals 0 for all x in this open interval AB, then f of x is constant on that same open interval AB. Okay, so let's talk about the proof for this theorem. Okay, so the first thing we're going to do is pick two values in that interval. Right, and we're going to pick them so that x1 is the smaller of the two numbers. Okay. It doesn't really matter, but we just need to know which one is smaller so that when we use an interval here, we know which one is the smaller one. Okay. Now, we want to try to use the mean value theorem on f of x. Okay. And we can't use it right away, right? We know that f prime of x exists on the open interval AB, right? So we could potentially just say, okay, well, that checks off part 2. We know that f is differentiable on AB, okay? And in fact, we know that f is differentiable, or because we know that f is differentiable on the open interval AB, we also know that f is continuous on the open interval AB, okay? But we don't know that f is continuous on the closed interval, right? Meaning we don't know that f is continuous at the endpoints. And that's so important, as we saw in an example in a previous video, okay? So that's why we need to look at x1 and x2, okay? So since f is differentiable, well, even more basic than that, right? Since f prime of x is 0 on AB, right? We know that f prime of x exists on AB, okay? Okay, so since f prime of x is 0 on AB, we know that f is differentiable on AB. Okay? Remember, being differentiable is a more strict condition than being continuous, right? If a function is differentiable, then it must also be continuous, right? So f is also continuous on AB. Right, on the open interval AB. Okay, so like we talked about, this is almost enough to just apply the mean value theorem to the interval AB, but we don't know that f is continuous at the endpoints, so we can't just apply this theorem. Okay, so what we need to do is talk about the interval x1, x2. Right? This interval is in the interior of the open interval AB, okay? right? We can say it's contained in AB. Right, in the open interval AB, meaning that the endpoints x1 and x2 are inside the open interval, right? These endpoints x1 and x2 are not the endpoints A and B, okay? Right, so this tells us that F is continuous on the closed interval x1, x2, right? Because those endpoints, x1 and x2, again, are on the interior of this interval. So we know that the function is continuous there on that interior, right? These points, x1 and x2, they can't be A and B. So we don't have this issue with continuity at the endpoints. Okay, and F is differentiable on the open interval x1, x2, it is differentiable on the open interval AB, but it is more specifically differentiable on the open interval x1, x2. Okay? So what that means for us is there exists a C in x1, x2, that interval, so that, right, we're concluding the conclusion of the mean value theorem, right? F prime of C is equal to f of x2 minus f of x1, right, over x2 minus x1. Okay? Now, we know that f prime of C is 0, right? Because we know, it says it right here, right? F prime of x is 0. So f prime of C has to be 0. Okay, I'm going to use cross multiplication, right? So this tells me that 0 is equal to f of x2 minus f of x1, okay? Which means that f of x2 is equal to f of x1, okay? So this means for any 2 points, right, in this open interval, their y values are the same, okay? So for any 2 points right, f of x2 is equal to f of x1, okay? And this is exactly what it means for the function to be constant, right? That all of the y values are equal to one another. Okay? So that is the proof of that theorem. Okay? All right, so let's look at what's called a corollary, okay? So a corollary is something that is considered a very close result, right? Something that's very similar to the result of the theorem, right? Or something that follows immediately from that theorem, right? Something that is really easily proved using the theorem. Okay, so let's look at what our corollary is for this theorem. Okay, and then we'll prove it using the theorem that we just looked at. Okay. Okay, so what is the result that follows immediately from this theorem? Okay, if f prime of x equals g prime of x, for all x in an open interval a, b, then f minus g of x, right, is a constant. Okay, and in more plain language, we should say a constant on AB specifically. Okay, and perhaps more constructively, right, we can say that f of x equals g of x, right, plus some constant c. Okay. Actually, let's go ahead and change this to a k because we don't want to get confused with the c that's in the mean value theorem. Okay. So this can be a lot more helpful when you're trying to do proofs, is the idea that if the derivatives are the same, then the difference in the functions is a constant. Okay? Or one function is the other function plus some constant. Okay? So let's go ahead and look at a proof of this. And remember what I said, this should follow pretty closely from the previous theorem. Okay? So we're going to go ahead and define a new function h. Okay, and we're going to define it to be f minus g. Right, so f of x minus g of x. Okay. Then we know what h prime of x is, right? It's f of x, right? F prime of x minus g prime of x. Okay? But we know, right here, that f prime of x and g prime of x are equal. Right? H prime of x, right? If these two things are equal, when we subtract them, we get 0. Okay? Okay. We're going to specify that this is true on the interval AB. Okay, so we have that h prime of x, right, is 0 on AB. Okay, now we're going to use this first theorem, right, to find a conclusion. So f prime of x, right, in this case we have h prime of x is 0 on that open interval. Okay, so by the theorem, h of x is constant on AB. Okay. So h of x equals k for some constant k. On AB. Okay, so that would mean h of x, which is f of x minus g of x, is equal to k, right, on AB. And what that tells us is that f of x is equal to g of x plus k on AB. Exactly as we were hoping for. Okay? All right, so there's the theorem and its corollary. Okay? This can be really helpful for some things that are more constructive, right, in terms of finding out what f of x and g of x look like. Okay, so let's go ahead and look at an example of how to use this theorem, or maybe its corollary. Okay, now that we've seen the proofs, I'm going to leave the theorem and its corollary there. So f of x is 1 over x. Okay. And g of x is going to be a piecewise defined function where it's 1 over x if x is greater than 0. Okay. And it is 1 plus 1 over x where x is less than 0. Okay. Now let's go ahead and look at what the questions are. Okay. So we're going to show that f prime of x is equal to g prime of x. On their domains. Okay, so let's go ahead and do that. So f of x is x to the minus 1, right? So f prime of x is equal to minus x to the minus 2. Okay, right? We could also say that this is minus 1 over x squared. Then let's look at g prime of x, right? And again, this is going to be given in piecewise form, okay? So for x greater than 0, we are going to get exactly what we have here, minus 1 over x squared. And for x less than 0, right, we're going to take the derivative of 1, which is 0, and the derivative of 1 over x, which is minus 1 over x squared. Okay? All right, so there's our derivatives for these two things. Okay, so we can see that these two things are equal, right, on their domain. Okay. All right, so let's look at the second part of this question. Okay, so part B, this is asking us, can we conclude that f of x minus g of x is a constant. Okay. Now, first of all, let's look at what f of x minus g of x actually is. Okay, so this is going to be a piecewise function, right? Because it depends on what g of x is, right? So if g of x is, or if x is greater than 0, then f of x is 1 over x, and g of x is 1 over x. Okay, so this is f minus g. If x is less than 0, okay, then we have f of x, which is 1 over x, minus g of x, which is 1 plus 1 over x. Okay? So this would say that f minus g, right, or f of x minus g of x is 0 for positive values of x and negative 1 for negative values of x. Okay? So can we conclude that it is a constant? No, absolutely not. You can see that it is not a constant. It is two different values here. Okay? But why not? Right? We did conclude that f prime of x and g prime of x are equal to one another, right? So the issue lies with this statement. Okay? We have to have an interval that we're talking about, right? And you can see that we snuck this in here by saying on their domains. Okay? So how do we resolve this? How do we explain why these two things aren't equal, right? Why is the difference between them not a constant? Okay? And like I said, the issue really has to do with this statement on their domains. Okay? So we would need an interval, okay, to talk about. I should say f of x minus g of x, right? Not just f minus g. Okay. So the answer is, right, that f of x minus g of x would be a constant for any interval in their domain. Okay? Their domain does not include 0. Okay? So the difference between them is a constant for any interval that does not include 0. So it is very important that when you think about this theorem and its corollary, right, it's not telling you that the two functions differ by a constant everywhere, right? They only differ by a constant in these intervals, right, where both of their derivatives are equal, right? And in this example, we can see that that does not include x equals 0. Okay? All right, I will see you guys in class.